Hello and welcome back to my Physics 100 class. Today we will discuss about magnetism. Magnetism is very important to our daily life. Almost 70% of our technology depend on the magnetic material, from electricity, transportation vehicle, airplane, medical instrument, sensors, smartphone, etc. All depends on the presence of magnetic materials. The picture of the globe above shows the map of the geomagnetic field, which is very important for navigation, mineral exploration, disaster mitigation. Even the migration of birds depend on their ability to identify the place and direction based on their magnetic field. Historically, the magnetism phenomena first recorded in Magnesia region, in ancient Greek region, now in modern day of Turkey. Stones move unattracted with each other. These stones later called as magnet. Magnet has two poles, north and south. Like poles will repel with each other. Unlike poles, attract with each other. The origin of magnetism in a material comes from a microscopic source, that is, the spinning electrons. Electron spins in the counterclockwise direction produce a spin-up orientation, or we call it as a north pole, while electron spins in the clockwise direction produce a spin-down orientation, or south pole. Atoms with the same orientation of magnetic fields produce a magnetic domain. Each magnetic domain is composed of billions of atoms with the same magnetic field orientation. In the normal or unmagnetized condition, the orientation of magnetic domains are random. In the magnetized condition, the orientation of magnetic domain are more uniform. The first encounter of electricity and magnetism phenomena was first discovered by Danish physicist named Hans Christian Ørsted. He had found that when the compass needle is positioned below a straight wire carrying a current, the direction of the needle is deflected. Now let's take a look at the picture on the right side. When there's no current, the direction of the compass needle is uniform. But when you let the current flows in a wire, now the direction of the compass needles will be different at each point. If you track the direction of each needle, it will create a circular path of magnetic field. We call this phenomena as the right-hand rule, as shown in the figure below. The magnitude of the magnetic field around a current-carrying wire depends on several factors. First, the amount of the current flowing in a wire. Second, the distance from the wire to the point of measurement. And third, the media around the wire and point of measurement. The bigger the current is, the bigger the magnetic field produced at that particular distance are. So, the magnetic field depends proportional to the magnitude of the current. The further the distance r from the wire is, the smaller the magnetic field measured at that point. And the closer the distance from the wire, the bigger the magnetic field measured at that point. So the magnetic field B is simply inversely proportional to distance r. But since the magnetic field at distance r has a circular path, we put the circumference of the circle 2 pi r in this equation instead of r. B is also depend on the media around the wire. For the open air, we have a constant mu naught, which is the magnetic susceptibility of vacuum. This is called as a Biot-Savart law. B is equal to mu naught I divided by 2 pi r. The direction of a magnetic field at a distance r from the wire is perpendicular to the vector radius r. So we will have an infinite number of the magnetic field direction circling around the current carrying wire. When a charge is moving under the influence of the external magnetic field, it will experience a magnetic force called as a Lorentz force. This magnetic force is dependent on the charge q, the velocity of the moving charge v, the external magnetic field P, and the angle theta between velocity and the external magnetic field. This magnetic force is dependent on the angle between the direction of the movement or the direction of velocity and the direction of the magnetic field P. If the direction of the magnetic field is parallel in the same direction or anti-parallel in the opposite direction with the external magnetic field, no magnetic force created, since sine 0 and sine 180 degree is 0. We can use the right-hand rule number 2 here as shown in the figure below. By using your right hand, the direction of current is indicated by your thumb, the direction of the magnetic field by your index finger, and the direction of the magnetic force produced by the middle finger. As a convention, the direction of the current is actually the same with the direction of a moving positive charge. The equation of F equal to QVB sine theta is for a single charged particle. What about if we have a flow of many charged particles or we have a current? We can make a simple modification on the right-hand side of the equation by simply divide delta Q by delta T and multiply V with the delta T. In that way, you don't change anything in the equation. And as you know, delta Q divided by delta T is the current I, and V times delta T is the length of the wire. Then finally, we can rewrite that equation into F equal to ILB sine theta, or simply people just say F equal to Bill sine theta. If we have two wires, each carrying current I1 and I2, the first wire will create a magnetic field around its surrounding, and this magnetic field will produce a magnetic force on the second wire. The same thing happens at wire number 2. I2 will create a magnetic field at its surrounding and produce a magnetic force on the first wire. If those currents, I1 and I2, have the same direction, those wires will attract with each other. If they have an opposite direction of current, they will repel with each other. The magnitude of force per unit length experienced by each wire is calculated by this equation. F per L equal to mu naught times I1 times I2 divided by 2 pi r. To show the intensity or the strength of a magnetic field, we define a magnetic flux term. This magnetic flux is the total number of magnetic field lines which penetrate a particular surface area. Phi is A times B cosine theta, with A is the area of the surface, P is the magnetic field, and phi is the magnetic flux. If the direction of flux is parallel or in the same direction with the vector normal of the surface, the amount of the flux is maximum. This is because cosine 0 degree is 1. But if the surface is slightly rotated, less magnetic flux will penetrate the surface, so the total flux penetrate into the surface will decrease, and shown from the equation phi is AB cosine theta. One example of magnetic force application is the galvanometer. Galvanometer is simply a device to detect the current. When there's a current flowing through the loop and exposed to the external magnetic field, like shown in a figure on the left side, it will create a magnetic force. Since the loop is pretty much circular, the current on the left side of the loop will produce a different direction of force as compared to the force created by current on the right side of the loop. This pair of magnetic force will create a rotation or will create a torque. This torque will deflect the galvanometer's needle. Since we put a spring, this deflection is stopped by the spring at a particular scale, which indicates the amount of the current detected. Other example is the electric motor. The mechanism is pretty much the same like galvanometer, unless we didn't put a spring. That way, the motor will keep rolling due to the rotational force produced by a magnetic force pair. We have learned how the electricity or current produce a magnetic field. Now the question is, would the reverse also true? Can the magnetic field produce electricity? This question is answered by Michael Faraday through a magnetic induction experiment. Assume that we have a coil of wire connected to the galvanometer. When a magnetic field from a magnet bar exposed to the coil, there's no current produced or detected in the galvanometer. But when the magnet is brought closer to the coil, a small deflection observed in the galvanometer indication a current is produced in the coil. When the magnet is taken away from the coil, again the needle is deflected, but with a different direction. The faster you do this, or move the magnet back and forth in front of the coil, the bigger the deflection or current created. Faraday concluded that this electromotive force, or epsilon, this is actually is a voltage or potential difference, produced by this induction is proportional to the number of coil and also proportional to the rate of magnetic flux change, delta phi divided by delta t. The negative sign indicates that the current or potential produced by the coil is purposed to resist the magnetic field penetration from the external source. So we have the exercise here, so you can do exercise above as an example. If we have a rotating coil, the electromotive force induction produced will be NBA omega sine theta. The voltage or current produced by this generator is called as an alternating current. Now let's do some exercise. In this exercise, we have a problem like this. A straight wire is carrying of 2 amps of current. So you're asked to find the intensity of magnetic field at point P, the direction of magnetic field at point P, the intensity of magnetic field at point Q, and also the direction of magnetic field at point Q. What you need to do here to determine the magnetic field intensity, you just need to use the Biot-Savart law. P equal to mu naught I divided by 2 pi r. Putting all this number, so the intensity of the magnetic field at point P is 2 times 10 to the minus 7 Tesla. And to find the direction, you can use the right-hand rule, the first right-hand rule. So the direction of the current is following your thumb, and the direction of the magnetic field following the circular path of your four fingers. So the direction of the magnetic field at point P is outward from the plane, or it goes to you, goes to the reader. And for point Q, the intensity of magnetic field at point Q, again using Biot-Savart law, P is equal to mu naught I divided by 2 pi r. R for point Q is different as compared to point P. So putting this number in, all those number in, so we end up with this magnetic field intensity, 4 times 10 to the minus 7 Tesla. And again, using the right hand rule number 1, so you can determine now the direction of the magnetic field at point Q. And the direction is inward to the plane, or goes into the paper. Exercise number 2. We have a problem like this. An electron, remember electron has a negative charge. An electron with the charge of 1.6 times 10 to the minus 19 coulomb moves with this velocity 5 times 10 to the 5 meter per second under the influence of 0.8 Tesla magnetic field. Find the amount of magnetic force experienced by the electron and the direction of the magnetic force experienced by the electron. To find the amount of the magnetic force, you simply just use F equal to QVB sine theta. So if the direction of the electron and the direction of the magnetic field is 90 degree, or they're perpendicular with each other, so sine theta just 1. So the maximum force experienced by this electron is F equal to QVB. Putting all those numbers in, F is equal to 6.4 times 10 to the minus 14 Newton. And to find the direction of the magnetic force, so you just use the right hand rule number 2, IBF. The direction of the current I following the direction of the thumb, the direction of the magnetic field following the direction of the index finger, and the direction of the force following the direction of the middle finger. So because you have an electron negative charge, so you just need to reverse the direction of the current. So instead of, if the direction of the current is up, so you have to reverse it to down, because instead of dealing with the positive charge, now you have a negative charge. So if you do that, the direction of the electron is toward the reader. So you can look at this picture. I've already put the picture here. Use your right hand and just follow the instruction in this picture. The last exercise is like this. If we have a wire with PQ with the length of 20 centimeter, this wire is moved from left to right. Of course, when the wire is moved, the number of magnetic field lines, or the number of flux, will increase because the area now increase. The wire is moved with the velocity of 6 meters per second. If the magnetic field induction B is 0.5 Weber per meter squared, then the current flows through the resistor is. So when you move the wire, so the number of flux penetrating this area will increase. So that will create the electromotive force E. E is B times L times V. And because now you have a closed circuit, you have a resistor R from the Ohm's law, epsilon or V voltage equal to I times R. So to solve this problem, so you just need to equate this equation BLV equal to IR. And if you solve for I is equal to BLV divided by R. Putting all those numbers into that equation, you end up with this answer, 0.3 amps. Okay, that's the lecture for today. Hopefully, you can get some idea about the magnetism. You still need to do some practice. Thank you very much.